Hey everyone, and welcome to the AI Anatomy Lab for an explainer on the absolute cutting edge of the 2026 machine learning frontier. I'm so excited to get into this today because we're going to bridge a really critical gap. We're moving past just calling a library API, and we're actually going to unpack the brilliant, often totally hidden mechanics running underneath our models. The fundamental truth for any machine learning practitioner right now is that the most interesting problems, the real breakthroughs, live exactly in this gap between importing well and understanding deeply. So if you want to know what's actually powering the next generation of AI, you are in the exact right place. Let's dive in. Here is our roadmap for today. 1. The deep understanding gap. 2. The 2026 architecture frontier. 3. Inside the black box. 4. Hidden mechanics you use. And finally, 5. The future of inference.
Let's kick things off with Section 1, the deep understanding gap, imports well versus understands deeply.
Moving into Section 2, the 2026 architecture frontier, beyond the bigger transformer.
Okay, so if you look at the 2026 frontier of machine learning, you'll immediately notice the trend isn't just about brute forcing a bigger transformer anymore. We've officially moved past that. Instead, we're seeing this massive architectural pivot toward hybrid models. Basically, architects are alternating regular attention layers with linear or state space layers. Take Nematron 3 Super as an example. It mixes standard attention with Mamba-2 layers to become wildly more efficient at processing really long context. And on the flip side, you've got models like Qwen 3.6 utilizing gated delta net layers for their non-attention portions. We are fundamentally rewiring the basic building blocks here.
And this push is so intense, there's literally a paper called Attention to Mamba, a recipe for cross-architecture distillation. It perfectly highlights what researchers are obsessed with right now. They aren't just building hybrids, they are aggressively hunting for the optimal ratio of attention to state space layers. It's all about figuring out how to take a massive, expensive attention-only model and mathematically distill it down into a highly efficient hybrid form. Which naturally brings us to a huge question about how we actually train these massive structures. Like, what if we treated weight matrices like actual geometrical structures, instead of just a loose collection of independent scalars? This is one of the most underrated yet totally revolutionary shifts happening right now. It's a complete rebellion against the standard atom optimizer we've all relied on for years. Meet the Muon optimizer. Now, standard optimizers like atom treat every single weight as an independent number, right? But Muon is completely different. It's geometry aware. It recognizes that weight matrices have a real geometric structure, so it performs steepest descent under the spectral norm. And it pulls this off using a really clever mathematical trick called the Newton-Schultz iteration to orthogonalize the updates. Basically, by approximating the matrix sign function with a cheap polynomial iteration, instead of doing an incredibly expensive singular value decomposition, Muon efficiently respects the true geometry of the weights. So, you're probably wondering, what does that geometry-aware math actually get you in practice? Well, scaling law experiments show that Muon achieves roughly double the computational efficiency compared to AtomW at compute optimal training. Let that sink in. That is a staggering 2x performance gain simply by respecting the mathematical shape of the matrix during optimization. And because of that massive gain, this breakthrough has ignited a live research race. We've got a whole ecosystem of follow-ups popping up right now, all trying to figure out the absolute best norm to optimize under cheaply at scale. You've got Newton Muon adding curvature info, Dion doing distributed orthogonalization, and Polar Express searching for even better matrix sign methods. It's just a thrilling time, especially if you're a fan of numerical linear algebra, because it directly impacts exactly how fast and how cheap we can train future models. All right, on to Section 3, inside the black box, interpretability and parameter budgets. Let's shift gears to how we construct and interpret the inside of this black box, starting with a very practical question. How exactly do you spend your parameter budget? For the longest time, with mixture of experts or MOE models, the default assumption was just to dump your parameter capacity mostly into the expert feed-forward networks. But new findings are completely upending those long-held assumptions. There's this recent paper called Scaling Embeddings Outperforms Scaling Experts in Language Models, and it suggests our budgets might be vastly better spent scaling the embedding tables themselves. It just rips open this massive problem space for how we allocate parameters across embeddings, attention, and experts. But here's the catch. Once we allocate those parameters and actually train them, how do we know what they are thinking? How do we find true, interpretable concepts inside what is basically a neural superposition soup?
Trying to understand these parameters leads us right into the absolute thick of the mechanistic interpretability debate. The current weapon of choice for untangling this is the sparse autoencoder, or SAE. SAEs basically try to decompose a model's dense, tangled internal activations into sparse, monosemantic features. Basically, the goal is one feature equals one understandable concept. They want to pull interpretable concepts out of the raw activations. But the epistemic uncertainty here is just off the charts. Right now, literally half the field sees SAEs as a genuine, monumental breakthrough for AI understanding, while the other half argues it's totally a leaky abstraction, mainly because these features sometimes aren't even consistent across different training runs. And when you do start digging into these activations, you find some seriously wild phenomena. Take this fascinating paper, The Spike, the Sparse, and the Sync. It explores why a handful of tokens, very often literally just the first token in a prompt, accumulate these massive, towering activation magnitudes. They turn into attention sinks that the model completely relies on to keep its internal stability in check. And this is super practical stuff. If you work on quantizing models to INT8 or FP4, these massive attention sink spikes are the exact anomalies that will completely break your naive quantization math. Which brings us to Section 4, Hidden Mechanics You Use. Welcome to the Hidden Engine Room. Let's actually go down into this hidden engine room and look at concepts that sit inside practically every single machine learning library call you make. These hidden depths are full of incredibly elegant tricks that we use daily but rarely stop to derive. Take rope, rotary position embeddings. It encodes position by literally rotating query and key vectors in 2D subspaces, so their dot product strictly depends on their relative position. It's beautiful math. Or think about the softmax stability trick, this deceptively simple operation where you just subtract the maximum value before exponentiating. It looks so trivial, but it's the exact magical reason your library doesn't just silently crash and throw NaN errors during training. These are the true unsung heroes of our everyday code. Now, let me throw a question at you. When you run inference, why is text decoding actually bounded by memory bandwidth rather than raw compute power? Answering this one single question explains the physical traffic jams that are shaping almost all inference-serving engineering happening right now. The culprit here is the KV cache memory wall. When a model is generating text, for every single new token it produces, the system has to reread the entire key value cache. Think about that. You're essentially rereading an entire library just to write down one single new word. So your GPU's massive compute cores are just sitting there idling, twiddling their thumbs, waiting for data to travel from memory. And remember those massive attention sink spikes we talked about a minute ago? Yeah, they make managing and compressing this cache incredibly painful without destroying the output quality. And this insane memory bottleneck is exactly why flash attention is such a brilliant systems algorithms crossover. A lot of people think flash attention is just a new math formula for attention. It's absolutely not. Its core insight is algorithmic I/O awareness. It mathematically tiles the computation to minimize those brutally expensive reads and writes between the GPU's main high-bandwidth memory and its super-fast SRAM. It is a straight-up data tiling masterclass, designed entirely to beat that memory wall. Finally, Section 5, the future of inference, reasoning and decoding. So if we want fast, stable inference going forward, we have to look at the massive shifts happening in reasoning models. If you peek at the reinforcement learning recipe behind these breakthrough 2026 models, the shift is obvious. The industry is dropping PPO, which was annoying because it required training a whole separate learned value network just to act as a critic. Instead, everyone's moving to GRPO, Group Relative Policy Optimization, or RLVR. This method just uses the average reward of a group of sampled completions as the baseline. It's way cheaper to compute, it's vastly more stable, and it completely throws out the need for that extra critic network. We're also attacking those inference memory bottlenecks with this incredibly elegant technique called speculative decoding. Here's how it works. A really small, fast draft model proposes a sequence of tokens. Then, your massive, slow model just verifies those tokens all at once in parallel. Because of a beautiful mathematical rule called rejection sampling, this little three-step dance makes inference vastly faster while remaining provably lossless. You get the exact same output distribution as if you only ran the big model, just in a fraction of the time. And lastly, even something that sounds as simple as weight tying, which is where you share the input embedding matrix and the output projection matrix, goes way beyond just saving a few parameters. Mathematically, it fundamentally restricts the rank constraints on the shapes the model can express over its vocabulary distribution. It's a foundational structural choice that dictates the very mathematical limits of what your model can actually output.
Which brings us to the end of this explainer. As you wrap up and get back to your code today, I really want to leave you with this one thought. When you write your next API call, are you just going to import well, or will you take the time to understand deeply? Push past that surface level, grasp the geometric structures, the memory walls, and the raw architectural realities quietly running inside your models. Because the real magic isn't in the library, it's in the math underneath. Thanks for exploring the frontier with me today. Stay curious and keep digging deeper.